Good afternoon, everybody. I'm just going to wait a moment for all the attendees to join the webinar before we start the presentation for today. Okay, thank you again for everyone for joining this webinar today and to join us to listen to some of the entries for the competition for the Davidson Inventors Challenge. My name is Cameron Yunus. I'm an associate teaching professor at the Department of Chemical Engineering, and I'll be hosting the webinar today. Just to kind of run through some etiquettes of what's going to happen in the webinar, just so you're aware that this is a webinar where people are joining as an attendee. If you are an attendee, please note that your cameras and mics will be automatically off. If you have any questions that you'd like to post during the webinar, you can use the Q&A feature, which is available on the Zoom bar toolbar at the bottom of your screen, and post any questions there for any of the presenters. And I should be able to then host those questions and pass those questions on to all the presenters at the end of their presentations. The other thing to note, panelists can actually turn their videos and mics off. If a panelist isn't presenting, please make sure your video and mic is off during the Zoom webinar. And just for reason of safeguarding, if there are any concerns for regards to safeguarding or any issues with moderation, please note the designated safeguarding lead at the department is Elena Gonzalez, and her contact details are there. All right, so just to kind of talk a little about the actual competition, it's been one that's been running for a number of years now. There's a lot of people who've been supporting this event, this outreach activity, and just really wanted to take a moment to thank all the people involved. So we have ASTI, who is an organization in Malaysia, who have been very helpful and supportive in helping us establish this competition. As well as that, we've always had to support the IChemE, who have always been able to endorse this event and provide the support for this as well. So I just wanted to say a big thank you to them for all their help and support. The other thing I would like to say is a big thank you to all the participants. We had over 100 entries for the competition, a number of students who schools entered the competition. Lots of interesting sort of entries were sent in. So many thanks to all those students who were engaged in this program and all their hard work. And it was great to be able to read all of the work that they've been researching around the subjects that they're interested in. The other thing I just wanted to say is to thank all our reviewers and mentors who helped look through all the entries that came in and provide feedback to all the students who entered the competition. And last but not least, I just wanted to thank our special guests who joined us today, Deborah and Nigel. Many thanks for your time today, and I hope you enjoy the presentations which are shortly to follow. So without further ado, just to explain what's going to happen, we'll have a short welcome from our head of department, Professor Clemens Kaminsky, and then I'll be passing on to Peter Davidson, who will be telling you a little bit about Professor John Davidson, who was an eminent professor at the Department of Chemical Engineering. After that, we will move on to our presentations, and we have 4 finalist speakers speaking, who will be telling you about some of their research projects that they've been doing. At the end of these short presentations, there will be a short break for 10 to 15 minutes where the judging panel will be deliberating on all the presentations. And then after that, we have our keynote speaker, Deborah, who will be presenting you some of her experiences as a chemical engineer and the journey she's had as a career in chemical engineering. And then at the end, we will have some closing remarks from Nigel, who's the president of the IChemE association. So brilliant. Thank you so much for everyone for joining. Without any further ado, I'm going to pass over to Clemens to do a quick welcome.
Well, thank you, Cam. Can you hear me okay? Is the sound okay? and you can see me as well. That's not so important. So a very, very warm welcome, literally very warm. My office is sweltering today. It's a shame I can't see you all in person. I would have loved to actually welcome you all in person, but it's first of all, biggest welcome to the 4 teams who are in this final. It's exciting, of course, for all of you, this event, and finding out who will go home with the big prize. But for me, you are all winners already, having participated with such fervor and with such brilliant ideas, trying to make a difference. The energy and the brilliance of the submissions that we've received made it really, really hard actually to shortlist the 4 teams presenting today. So well done for actually getting this far, but also well done for taking a real interest and trying to make a difference, trying to do something about big challenges. I hope you learned a lot, and I hope that this inspires you to perhaps consider doing the sorts of things that we do professionally as chemical engineers and biotechnologists. In fact, what we're doing is not so different to what you have attempted to do in your projects. I will say a bit more about our department and about the discipline. But before I do that, let me also welcome the speakers today. Nigel Hurst from the IChemE and Deborah Grubb from the American Institute of Chemical Engineers, and also Peter Davidson, the son of John Davidson, in whose name this challenge is taking place today and has been for a few years. Peter will tell you more about John, but I would just like to say John Davidson, Professor Davidson, we called him affectionately the old prof here in chemical engineering. He was a true giant of a chemical engineer. Is possibly one of the most famous chemical engineers ever to live. And he worked here, and he worked very much with young people. He had a real interest in getting the next generation of brilliant scientists through to the next stage. He would have been absolutely delighted to see your contributions and to see you thrive and to see your ideas. So this really is in the spirit of his legacy. So, but Peter will tell you more about John in the next talk. Again, like Cam, my thanks to the IChemE and ASTI for supporting this, and also our alumnus Yunus Yassin, who in fact is the initiator of ASTI. And a very, very big thanks go, of course, to the organizers of this great event, Eleanor and Cam. Thank you both, and the many mentors and students here in the department who actually made this possible and actually went through the submissions and looked at the quality and fed back to us. So what is chemical engineering? What is it that we do in our department? It's a shame that you can't be here in person. I mean, you would see the building that Cam had on the slides earlier on. It's a lovely new building, which was we've been in this building for maybe 6 or 7 years now. It's a brand new building. It was very expensive to build. It cost something like 70 million to build up, and the reason for that is because it contains very advanced laboratories to essentially allow us to do the research that's the brilliant people who are here and that I have the pleasure of working with and collaborating with in this department here, to allow them to do their work. So in a nutshell, what we are trying to do is we are trying to do science that allows us to tackle big global challenges. It's not very different to what you are trying to do. So the challenges that we set in the DIC challenge, they are within the they're set within the challenges that are set by the UN Sustainable Development Goals, as you know. And so we are trying to do the same. So I think of chemical engineering and biotechnology and of the work that my people here do as trying to understand processes from the molecule up, having fundamental understanding knowledge, the sort of knowledge that physicists generate, that biologists generate, that chemists generate, understanding how things work really at the most fundamental level. But what's different to a pure chemist, a pure physicist, or a pure biologist is that we take this knowledge and we're not just content with understanding, we want to turn this knowledge into real materials, into real products, into real processes that make our environment and our world a better place to be in. So making products efficiently with less waste, converting energy in a better way, finding chemical processes that are sustainable. These are the kind of things that interest us, and these are the sort of things that drive us. And so we have in our building a whole range of experts in different disciplines, and we bring them all together to do this kind of work where we try to really come up with ideas that make a difference. I mean, to give you one example that you all understand, if you take the vaccine, for example, that was produced to help us get out of the crisis caused by the pandemic, that's one such process where to come up with an mRNA vaccine, you have to understand the process well enough so that you can coax the cells in your body to make a part of the virus that causes you harm. But that part must, of course, not be toxic. So you really need to have a molecular level understanding of that. But so you deliver a bit of RNA into your body, but you have to get it in there somehow. So you have to understand the transport of this. It's not enough to just understand the process itself. You need to be able to package the drug that you make, deliver the RNA in such a way that it's taken up by the body, that it crosses membranes, that the biology is turned on inside the cells, and that you produce enough of that so that an immune response is generated in your body, and that then actually helps you prevent getting nasty side effects from the virus itself. And that's really what helped us. There's actually major chemical engineering knowledge going into this, and major biotechnology knowledge going into doing this stuff. It's not trivial at all, actually, to just make the RNA. You need to produce it in big tanks and in big quantities. That's not simple. You can do this in a test tube, but actually making this for billions of people is not a trivial task. Storing the vaccine so it doesn't go daft. I mean, you may have seen this in the news, was a real problem. It's chemical engineers who actually managed to deal with that storage problem as well, so that the vaccine can be distributed everywhere. So this just gives you the flavor. It's this and many other types of research like this that goes on in chemical engineering and in biotechnology. And in some way, this is really what you have done yourselves with your projects, trying to tackle difficult things. And you will have encountered many of the problems that we encountered too, in the work that you've done, in the research that you have done. So I don't want to tell you much more at this stage. I would want to pass on to Peter Davidson so he can give you an overview of John's life. But before I pass on, I wish you really good luck with the exercise. I really hope you had fun doing this, but I also hope that you learned something that will be valuable in your future careers and aspirations. And I really hope to see you in the future and I hope that we have with you the next generation of budding, brilliant chemical engineers and biotechnologists, and I would be absolutely delighted to welcome a few of you in our department. And I would also like to say that, John Davidson would have been absolutely delighted too. So with that, good luck, and on to Peter.
Thank you, Clemens. Well, I'd like to echo some of that, and just to say it's an honor to be here, and congratulations to all the finalists and others on the work they've done in getting here, and the interest of your projects. I've been asked to say a few words about my father, John Davidson, and chemical engineering in Cambridge. And by background, we were the only father and son fellows of the Royal Academy of Engineering, as well as being fellows of the Institution of Chemical Engineers. But I have to say he was somewhat more academically distinguished than me. He gained the Prince Philip Medal from the Royal Academy. I think the first recipient of that was Frank Whittle, who developed the jet engine, and the Royal Medal from the Royal Society, as well as being a Royal Society Vice President and a Vice Master at Trinity. For my background, I read engineering, then chemical engineering at Cambridge. I had a career in chemical industry in fertilizers, catalysis, pigments and flavors, and then was innovation advisor for part of the UK government, and have spent the last 15 years on startups. But back to my father, he didn't have an easy childhood, so I guess some of you have had difficulties on your way. He was born a bit earlier in 1926. His father died when he was 9, but he was the man about the house, and he supported his mother and his older sister from an early age as an engineer mending domestic artifacts. He also had memories of the Depression in Newcastle before the war, of men standing on street corners with nothing to do. But I'd say those early experiences softened his heart rather than hardened it. He almost left school before the sixth form, but he was persuaded by a teacher not to do that. And he described how uplifting it was to focus on the sciences, which he really enjoyed. As a hobby, he cycled with friends around the Northumberland Hills. He came from Newcastle. He went up to Trinity College, Cambridge in 1944, did the 3-year tripos in 2 and came top. And he believed in and often quoted the wisdom of Proverbs 15. A soft answer turneth away wrath, but grievous words stir up anger. But he was an optimist. He and my mother shared an optimistic view of the world, believing especially in the best of people, particularly the young. So he would be delighted to see you lot. They took pretty keen enjoyment in their family. They both had strong opinions, but I would say neither was bothered about ideas for their own sake. They cared about what difference ideas could make in practice, a slight echo of what Clemens has just said. So with humor and a lot of generosity of spirit, he developed the chemical engineering department over the course of a long career, widening its scope. So he brought in biotechnology to the department, and his motto was from the parable of the talents: use what you are given, which is one of my favorites. I remember him saying that when he joined the chemical engineering department, the university authorities were a little doubtful about the young discipline. It started just after the war. And one Nobel laureate, who actually discovered the neutron, explained to a lecturer in that young department then, there is no place in Cambridge for applied science. However, he carried on. He did a lot of work on bubbles and fluidization. That's been described elsewhere as an adroit combination of scientific theory and engineering experiment, and helped by his predecessors to establish the chemical engineering as, quotes, a proper discipline at Cambridge, and allowed the better understanding of many industrial technologies. And he built on the shoulders of many of the great Victorian Cambridge fluid mechanics community with groundbreaking analysis and elegant experiments. And those successes have been recognized by the world at large, but the medals he received were put away for safekeeping. Ostentation wasn't in his character. He was pretty persistent in the solution of problems and produced around 3 papers a year, for over 65 years until almost his last months. The quality was very consistent, and unless away from Cambridge, he would cycle to the lab at about 8 in the morning, have lunch in his college, return to work at the lab, cycle home at 6:30, possibly have a game of tennis with me, and then he'd put another hour or two at his desk after dinner, and then often a few hours overnight. He didn't sleep too well. But he wasn't desk-bound. He had a huge interest in how things work. He was a real engineer, not an engineering scientist. He used to be very critical of the academics who just did science and didn't make things. He had a substantial industrial consulting practice, and he contributed to the design of kit that created value, had elegance, and I'm interested in your projects, whether they have elegance, and if not designed correctly, you design kit that could kill people. He thought generally about that academic engineers should spend time in industry when young to understand what mattered in an applied subject. He supported my departure from Cambridge as a young graduate to what was then called ICI, it became AstraZeneca and a whole series of other companies, to apply what I had learned. And when others suggested that I should do research and a PhD should be undertaken, he said, no, get experience first in industry. His contact was not just for monetary reward, but for the challenge of the interesting problems he could contribute to. I found him almost wherever I went to in the chemical industry, that he had been there before me. I used to introduce him to problems that I knew he could contribute to, which was an extraordinarily happy partnership that I much miss. I never knew him to make a significant technical error. I remember him being overjoyed when somebody referred to him as my father, rather than me being his son. But his research and consulting never distracted him from his teaching. He used to say that teaching widens one's field of knowledge. Constant contact with clever students is stimulating, and their questions are invaluable. And I would say that to all of you. Don't hesitate to ask good questions. And it was his settled view that the value of Cambridge lay as much as being the development of young talent as in the research conducted. I have to say, Clemens and I have had a few discussions about that, about persuading the modern hierarchy that that's the case. Students commented on his rigor, which could often be perceived as terrifying, but was always administered gently. They often said years later that he taught them how to think. However, beneath that quiet exterior, he had a very human touch. With my mother, he entertained supervisees to dinner at home and held garden parties at the family home in summer for undergraduates, research students, and staff. Sometimes visitors' bikes were mended. I can recall with great amusement young undergraduates saying, my bike worked rather better after a visit to your father's home. He created a garden with my mother. He was an inveterate hill walker with a huge enjoyment of the Lake District and the Alps. And that eased stresses that are occasionally evident when he was head of department. Partly inspired by his mother's example, he was a very strong supporter of women professionals, and he had been delighted at the strong fielding of women in this competition. He was also a strong supporter of his friend John Bradfield's creation of the Science Park, which was the first science park in Europe, copied from the success of what had been going on at MIT and in California. And that's done an awful lot to bring universities closer to what he saw as the real world. And I'm always delighted when I see that chemical engineering at Cambridge has a role in some of those startups. But above all, he was devoted to the department and the college, and he was a quiet peacemaker in both. He had a great faith in the college and the department's future, believing that scholarship, subdued leadership, a cooperative approach, and the care and development of people would carry those institutions through without any formal strategy. He would be delighted to see the progress the inventors have made today and wish them very well for the future. He liked the comment one senior environmentalist made It's all very well for people like him to talk, but it was the engineers that would save the planet and create conditions for wealth and health. Or as Lord Brown, a previous president of the Royal Academy of Engineering, said, anything that God didn't make, engineers have built. His spirit would align very much to what Clemens has said. Real problems need real chemical engineering. Understand process and products from the fundamental and provide a holistic understanding. I would say, be jack of all trades and master of a few. The Cambridge chemical engineering degree has enabled people like me to argue with experts in almost all fields and hopefully develop better solutions, and it's fun. So thank you and good luck.
Thank you so much, Peter, for that. That was really insightful to hear about Professor Davidson's life. Now we're going to move on to the finalists to start their presentation. So I would like to invite sustainers to come turn on their mics and camera and share the screen with their slides to start their presentation.
Right, okay, hello everybody. We are the sustainers from Leicester Grammar School, and we are delighted to present our innovation to you all today. With growing concerns regarding plastic pollution, we have designed a model that is made to combat microplastic pollution in large bodies of water. Globally, governments, individuals, and organisations have begun to develop ways of removing existing plastic debris. However, recently we have begun to realise we discard millions of microscopic pollutants into our waters. Some countries have introduced bans on the use of microplastics in certain cosmetic products to increase, and we aim to increase similar prohibitions in other countries. Unfortunately, not much active progress has been made, and even if it had, it doesn't change the fact that there are currently 14 million tonnes of microplastics in the ocean at the moment. You might ask that by definition, microplastics are tiny, so why does that matter? But one of the problems is that we are largely unaware that we are using microplastics. For instance, every time we brush our teeth, the microplastics in toothpaste are washed into our water supply and mostly bypass current filtration systems. It is too early to fully understand the effects that these have on humans. However, preliminary evidence suggests that buildup of microplastics in the bodies of marine animals can lead to serious health issues, including neurotoxicity and behavioural abnormalities. From a lack of sufficient protein is how this is caused. Consequently, when humans consume seafood, these microplastics can build up in the body and cause organ problems. This is because microplastics are found everywhere, from the clean water that we supposedly drink to the fish in the sea. Having identified microplastics as a pollution issue, we decided as a team to come together and address this matter. We researched attempts to tackle plastic pollution that currently exist, and we identified two key steps within the process. Firstly is the removal step. The plastics must be removed from the water. While there are schemes being put into place to remove larger plastics, unfortunately, microplastics are not susceptible to current methods. Secondly, the plastics must be disposed of. This is currently done via three methods: incineration, recycling, or landfill. Incineration actually produces 2 tonnes of carbon dioxide for every tonne of plastic burn, so is not an environmentally friendly solution. Landfill is only a temporary solution, as the amount of plastic waste that we create easily overwhelms them, and it's not uncommon for microplastics to find their way back into the ocean via leachate. Recycling only accounts for 9% of all the plastics, and while it would be beneficial to recycle more of the waste that we produce, it is unlikely that this would be a solution which completely eliminates plastic waste. Oh, apologies. To address the microplastic pollution as a whole, we realized that we would need a system that combines both removal and disposal. In creating a solution to this, we aim to work towards 3 of the United Nations Sustainable Development Goals. The first one is Goal 6, clean water and sanitation. We aim to work towards ridding drinking water of plastic pollutants and ensuring people do not have to fear health problems from a basic necessity. The second goal is Goal 13, climate action. By safely disposing of these plastics as part of our model, we aim to reduce the amount that is incinerated, thus reducing the amount of carbon dioxide released into the atmosphere. And our final goal is life below the water. We intend to improve the living conditions of marine life as a result of removing plastic from the oceans. We aim to achieve these SDGs in context of the 5 Ps outlined by the UN: people, planet, prosperity, peace, and partnership. As our model aims to improve the ecosystem, lives of people, and provide a way to clean the water supply, we can share our model between different nations and reduce conflict about water sanitation.
We discovered the research done by Fionn Ferreira, which showed that microplastics could be removed from the water using ferrofluids due to the simple principle of non-polar oil particles attracting non-polar plastic particles. His results show that ferrofluids are effective for many different types of microplastics. Having found a solution to the removal stage of our process, our team started looking for a way to complete the disposal step. We initially looked into bacterium Ideonella sarcoides, as it's able to secrete an enzyme that degrades the plastic PET into environmentally harmless monomers. This seemed to be a promising approach. However, the bacterium only degrades PET, accounting for 29.3% of microplastics. As we wanted to target as many different types of microplastics as possible, we decided to reject the use of bacteria. After running across similar issues with different fungi and algae, our investigation turns towards photocatalytic degradation. Photocatalysts are semiconducting materials that, when exposed to light, modify the rate of a chemical reaction. When the photocatalyst is irradiated with a light of high enough frequency, it is able to oxidize organic compounds, such as plastics, readily. With a wide range of different photocatalysts available, we initially considered zinc oxide and zirconium dioxide. However, they were both dismissed on the grounds of higher costs and slower reaction rates than titanium dioxide. With titanium dioxide's ability to degrade trace amounts of the most common polymers found in microplastics, it can convert it into smaller benign molecules, as well as lower its cost and capability to break down plastics at a faster rate. And it has also proven to be the most viable option for our model. As the ferrofluid is being removed using a magnet, we decided to dope the titanium dioxide with ferric chloride to also give the photocatalyst mixture magnetic properties. This allows for all the chemicals to be removed from the water simultaneously and reused multiple times, making it sustainable.
With our method now in hand, we turned our attention to the creation of a practical, efficient, and largely automated system, as illustrated by our model. This includes 2 separate chambers. Firstly, a delivery pipe, which allows water to enter the water chamber before we release our ferrofluid catalyst mixture into the water. A propeller on the chamber floor, which isn't shown on this model but can be added, stirs or agitates the mixture, which ensures that all microplastics have come in contact with and thus are retrieved by the ferrofluid. Next, a robotic arm lowers an activated electromagnet into the water to attract our degradation mixture, thus completing the removal process, leaving behind clean water which can be released through a plug at the floor of the chamber. The robotic arm moves the electromagnet into the UV chamber, where the electromagnet releases the mixture. There, a roller spreads the mixture over a flat surface, which increases surface area and thus the rate of catalysis, before being treated with UV light in this chamber. This activates the catalyst in the mixture, resulting in the microplastics being broken down into water. This is the same process that occurs naturally to break down plastics. The process of photodegradation within our model takes approximately 5 hours, as opposed to the hundreds of thousands of years it would take for them to break down naturally. Finally, the flat face of the roller scrapes the treated degradation mixture back into the chamber, from which it can be re-released into a new batch of water in the water chamber, thus repeating the process. This ensures our invention recycles the chemicals used and reduces costs by eliminating the need for constant addition of the catalyst ferrofluid mixture.
Our initial model is designed to be a testing model that holds approximately 300 liters of water, which is about the same capacity as a full bathtub. We chose this amount as it is big enough to identify a sufficiently large concentration of microplastics that could be found in different water supplies, but small enough that we might be able to create a test model. We will use a pyrolysis GCMS and Raman spectroscopy in combination with our model to produce testing data on the reduction in the concentration of microplastics. Our initial estimate for the cost of producing this model is approximately £3,750. We formulated this estimate by using information on material prices based on supplier websites. Yet this would be massively reduced in a larger scale model. All in all, this cost is an initial estimate for testing model and would need to be revised in light of the environment it will be placed in and the scale of the model.
We were careful to consider that consumers exist all over the world when looking at how our model can be scaled. However, we decided that the most opportune place to implement the model initially is within water treatment facilities. The biggest advantage to this is that water is already collected for treatment and would remove microplastics from our drinking water. And as the ferrofluids and other chemicals we are using in the process are reused. This offers a cost-efficient and sustainable use of resources with a relatively low running cost. As consumers become more aware of the dangers of microplastics, there may be sufficient demand to create a household model that can treat tap water as well. Alternatively, larger models could be developed and attached to reservoirs and rivers, which would aim to tackle the larger problems within water supplies. Due to the vast number of ways that we could implement our design, further research would be needed in each scenario to give useful costing. We've also considered various adaptations to our model for future applications. This includes the addition of solar panels to provide renewable energy, reducing the running costs of the model. Different designs including multiple UV chambers, which could increase the volume of water filtered, and the implementation of analytical technology to allow the consumer to monitor and make improvements based on the environment of the model. In summary, we were able to produce a sustainable model that clears up microplastic pollution and helps provide clean drinking water and safer habitats for marine life to live in. We hope that in the future, we'll be able to partner with manufacturers and universities to create a physical prototype to carry out tests that will help us determine the most effective scale for our model. Our final ambition is to be able to implement this system as part of everyday water filtration facilities by making our model a cost-effective solution to removing microplastics that could be encouraged by government incentives. Thank you all for listening, and we welcome any questions.
Thank you very much, Sustainers, for your very nice presentation. I'm going to open this up for questions. If anybody has any questions, feel free to post them on the Q&A chat, and I can present them to read the questions out to the presenters. While we're waiting for any questions to be posted, I have a quick question for you guys. You talk about this sort of platform for cleaning up waters for microplastics. Have you guys thought about what sort of timescales it would take to try and process sort of a large volume of water, say a 300-litre tank that you were proposing?
So we have considered that the different stages of the whole process. The first stage, which includes the ferrofluid catalyst mixture mixing into the water and being removed by the electromagnet, should only take 1 to 2 days according to our estimates, because that's a maximum estimate depending on the strength of the electromagnet which we use. So we mentioned that that this model can be scaled. So if we use a larger electromagnet, we would be able to move it around more, and thus more of the mixture would be attracted, and thus can be moved to the UV chamber faster. We've considered the fact that we can use multiple UV chambers, which could increase the rate of degradation. And this can be done in a matter of hours rather than thousands of years, which could be taken through natural degradation.
Yeah, and just to clarify, the 1 to 2 days is for a larger scale model, is what we're estimating for a large scale model. For a small scale model like that, it could take a matter of minutes to hours. So as I say, that was our testing model, but we are aiming to implement this as a large system.
Okay, I've just had a question come through on the chat from one of the panelists. How are you taking into account the pH of the ferric chloride?
Well, with the ferric chloride having magnetic properties, all of the catalyst and ferrofluid mixture will be picked up along with the microplastics. As for the pH, I don't think it would have a big effect due to this. However, we do need to run our own tests in the various facilities that we'll be able to have with universities and manufacturers. So, yeah.
Okay. Okay, another question. Is there not a very significant problem on getting microplastics to the system? What fraction of the world microplastics would get to your system? Also, does the titanium oxide not generate carbon dioxide?
So we've demonstrated the various uses that we could implement the system in, one of those being water treatment facilities. So initially, our hope would be to target localized areas where the rate of microplastics entering facilities such as drinking water that's accessed by a lot of people. We hope to clean those areas first. Depending on how much we can expand our model and expand our scale, we hope to remove as much microplastic as possible from larger bodies of water as well.
We're also hoping to create a small scale model that can be attached to maybe households. So you can get clean drinking water into your household, because the water you'll get from your taps currently will contain some microplastics. So we realize that this will take some time, but every step that we can make just does count. In terms of the titanium dioxide releasing carbon dioxide, yes, it releases small amounts of carbon dioxide, very, very small amounts. But because we're using a closed system, we could use carbon capture methods within our model.
Yeah,
to
there's actually a company called Carbon Cure that captures the carbon and uses it in their concrete creation. So you don't actually have to use cement, which is the part of concrete that has the biggest carbon dioxide footprint. So it really does reduce carbon dioxide emissions, whereas, as Ellie said, it's in a controlled, closed environment and it is only small.
Okay, so I've got a couple of more questions here. One question's come through. Who is your target customer and what economic incentive do they have to invest in your system?
So initially, our target customer will be governments and large-scale organisations. We want to market it to water treatment facilities, but we feel like governments will be able to give some incentives based on the amount of money they are currently putting in to plastic removal out of the oceans. For example, at the moment, the Commonwealth is putting in approximately £10 billion into plastic removal. We're only looking for a fraction of that to come out to create our model on large scale. And so we're hoping for tax breaks or that kind of thing that would allow companies to buy our model. And then we hope that in time it will become a more relevant issue. More people will know that microplastics are a problem, and we can market it to smaller households that realize this.
And it's also important to know that with the modifications we plan to make, we can reduce the cost by quite a lot. So for instance, I mentioned using a stronger electromagnet that would reduce the cost that we need for a robotic arm to ensure that most of the degradation mixture can be attracted by having the large electromagnet rather than needing a robotic arm to move it around over a larger area.
Yeah, because we already found these costs from supplier chains. If we do it from a larger scale, it will definitely reduce the cost further, because it's also just a fraction of the cost that's currently being put into plastic removal.
Okay, we're running out of time, but I'm just going to ask one more question. Will the process contaminate the drinking water? Will it need further treatment?
No, so our whole process should be, so all of the chemicals that we put into our water are completely removed by the electromagnet. That was why we doped the titanium dioxide with ferric chloride in order to make it magnetic, so we could remove and reuse that, so we create a sustainable model. So it shouldn't contaminate the water, and you can just release the clean water after removing the chemicals. Okay,
great. I think we're now up for time. We should move on to the next presentation. Thank you very much for your presentation and for answering the questions. I'd now like to invite the next team to come online. And please turn on your camera and mics. This is Team Javelin. And over to you. You want to try again?
Yeah, sorry, the audio is not connecting.
We can hear you now.
Yeah. Okay. Can you hear us?
We can hear you, but we can't see your slides.
Can you see them?
Just press the slide onto the slides.
Can you see the slides now?
Oh, yes, you're on.
Okay, cool. Sorry. Okay, right.
Sorry about that. Thank you.
We're Team Javelin, and is it okay?
Ready? Go for it.
Okay, we're Team Javelin and we have invented a scheme of biodegradable contact lenses.
We approached this project with a view to tackle issues surrounding Sustainable Development Goal 12, responsible consumption and production. Cycles of production, consumption, and disposal are becoming increasingly unsustainable and, if not actively harmful for the prosperity of our planet, due to a lack of environmentally responsible behaviours. We were particularly concerned about the use of contact lenses, as a 2019 survey of 3,000 users revealed that only 3% attempted to recycle their lenses. Vision corrective lenses are used by over 4.2 million people in the UK, half of whom choose to use daily disposable lenses. These flexible lenses are often polymerized with non-renewable silicon monomers to maximize user comfort. Industrial waste processing, however, is ill-equipped to deal with these small lenses, which can contaminate clean batches of material and end up in water systems. Here, the silicon monomers contribute to microplastic accumulation through microplastic lens fragments that can threaten ecosystems through bioaccumulation. We aim to replace the current model with one that promotes responsible consumption and production by innovating a process that takes accountability for the full life cycle of the product and negates its potential for environmental harm at every stage.
So our solution is a subscription-based model of biodegradable lenses in which users that return their lenses are offered a discount on their next purchase. We researched and designed the lenses themselves, as well as the manufacturing and distribution processes, with a focus on minimizing wastage. The lenses are shipped out in a box containing a return slip and enzyme-embedded plastic bag that the user places their used lenses in. The lenses are biodegradable because instead of being made from petrochemicals, they are instead made from biomaterial, which is extracted from fungal cell wall material. This can be cultivated from commercially abundant bread waste. The enzyme-embedded bag is broken down with the lenses inside, so there is no issue with contamination and lenses slipping through equipment. Additionally, the specific enzyme breakdown mechanism and biohydrogel prevent any microplastic fragmentation, resulting in a completely broken down, harmless effluent. With regards to casing, we wanted to move towards a more circular usage of resources and materials, so we adapted an existing pattern of lens packaging in order to allow it to work within our model. To indefinitely reuse the aluminium in the packaging, we had to modify the design to remove plastic components. A key part of our project was ensuring the safety and the comfort of the user. We researched extensively and put great care into making sure our processes resulted in a sterile product. Through acid treatment and multiple rounds of autoclaving, we are confident that no living material can be found in the lenses.
In order to guarantee that our product works as intended, lots of research went into the scientific principles behind the properties and processes involved in our project. In addition to sterility, we had to ensure that the biodegradable nature of the lenses would not result in it degrading whilst in the eye. Comparison with other similar biomaterials, such as fungus-based textiles, led us to conclude that the lenses would not start degrading within the time frame of usage, as the temperatures required for the degradation are too high. The lenses would start drying out, as is the case with existing lenses, before degradation would become a problem. We also researched the physics behind lenses, optics, and the eye to certify that our lenses would be able to correct the vision of our users. The lens molding procedure we use in our model can produce the base curvature necessary to fully correct any type of vision problems. We designed various new processes that would allow us to create the material we needed, whilst ensuring that the scientific principle behind the processes was still valid. Change was needed with respect to some of the scales that the processes are carried out on. For example, hydrogel has only ever been extracted from fungal material on a laboratory basis, but in our model, we created an industrial scale continuous process that allows us to mass produce the hydrogel.
So what are the benefits of our model?
We felt that it was important to conduct a life cycle assessment on both the existing model of contact lenses as well as our own. In order to sufficiently address the sustainable development goal that we had chosen, it was important to analyze the impact of all stages of the life cycle of the product, especially since there could be effects that we had otherwise not been able to identify. In order to carry out the life cycle assessment, we split the contact lenses into multiple components and identified both negative and positive impacts of each stage. We tabulated the results as seen in this extract of our life cycle assessment. We used our main findings to inform the design of our product, which Jasmine will now talk about.
There are two main components to the current contact lens model, the lens and the packaging. Daily disposable lenses are made of a soft, hydrolytically stable hydrogel with a minimum 10% water volume and, as mentioned earlier, are often copolymerized with silicon monomers. Already, silicon is an energy-intensive material to extract with high competing demand for use in electronics. These lenses are sold as individually sealed polypropylene blister packs, suspended in a buffered saline solution and sealed with aluminium foil. The foil and polypropylene packaging must be separated before being put into their respective home recycling bins, whilst the lenses themselves are not recyclable from home. However, instead of putting them in general rubbish, many users choose to flush them down sinks or toilets for convenience. For every part of this existing product to be recycled, every part would need to be sorted, washed, shredded, and melted before extruding or forming into usable pellets. The improvements to our design focus on minimizing the potential for damage and maximizing convenience of disposal. In terms of logistical improvements, asking users to return their lenses and packaging allows us to take accountability for proper disposal. The biodegradable lenses and bag they are collected in are both decomposed under the same conditions, meaning the process is more time and energy efficient than melting or incinerating polypropylene. Our foil packaging can be recycled indefinitely, as long as we take care to maintain its purity, which is easily done by ensuring that it's returned for the correct industrial recycling. Another aspect of our improvements are to account for the possibility in which our model fails. In the event that a user continually forgets to return their waste, although they'll miss out on the discount offered to users who follow the scheme, we have tried to preemptively mitigate any negative consequences. The polyolefin lining that helps maintain sterility is 60% oxidogradable within 2 years once discarded. And given that the biomass hydrogel is entirely organic in source and thereby biodegrades, our product eliminates the possibility of contributing to microplastic accumulation.
In order to assess the impact of our design, it was important for us to consider how our project links in with the 5 Ps of sustainability. Contact lenses are used by millions of people every day, so our sustainable alternative allows them to tackle this issue on an individual scale. In terms of prosperity, the lack of silicon and petrochemicals allows them to biodegrade, eliminating pollution. As well as this, the recycling will reduce the issues associated with landfill, such as eviction as well as habitat loss. It is also worth noting that the lack of expensive silicon results in extra financial capital that can be invested into transport options that help the environment prosper, such as offsetting any carbon emissions associated with delivery. The renewability of our process and resources ensures that we have a limited impact on the planet and are not depriving future generations of any materials. This also means competition and conflict over finite resources is reduced and more peaceful relations can be encouraged. There is a huge element of partnership in our model, both between the customers and the process, but also between industries. Partnership with energy providers is highly adaptable, meaning we can easily progress with society as it moves towards more sustainable and renewable energy sources.
Though we have already thoroughly explored a whole host of possibilities with our lens invention, there are other avenues which may be worth exploring in the future. In the jump from laboratory synthesis to industrial manufacturing, it will be crucial to implement heat integration to ensure maximum energy efficiency and to minimize unnecessary combustion of fossil fuels. The efficiency may be further improved through partnerships with industries which can make use of our unwanted byproducts, as this would improve the process's overall atom economy. The biological hydrogel technologies involved in our invention could be repurposed in countless other applications, allowing many other disposable products to become more environmentally sustainable. We could also do more research into incorporating surfactants into our lenses to allow them to retain more moisture over extended usage periods to ensure they remain comfortable to wear. We could also experiment with what specific reactive concentrations produce the clearest hydrogels to ensure the lenses are just as clear and functional as any traditional lens.
So, in summary, our project allows consumers to make responsible choices with the products that they buy, which is becoming increasingly important as society shifts towards more sustainable consumer habits. The entire life cycle of our model is designed to promote circular usage of materials and avoid non-renewable resources, making it sustainable for future generations. We have used scientific basis to create technological innovation and improve and expand upon existing processes so they are better suited to meet the needs of our expanding population. Existing processes are constantly changing and improving with the introduction of new technologies, and this is no different in our project. The combinations of different manufacturing and chemical processes that have never been utilized together before allows us to create entirely new possibilities. Throughout our project, we had to evaluate competing factors such as economic, environmental, and safety, and making sure we prioritized effectively was a large part of the design process. We wanted our model to be realistic and something that would not require radical change to implement. In order to meet the sustainable development goal that we had selected and be generally sustainable, it seemed more fitting to make use of existing infrastructure and resources and set achievable goals that work in partnership with other efforts towards sustainability.
We would also like to acknowledge the parties involved in our challenge experience and give our thanks to the University of Cambridge, the Association of Science, Technology and Innovation, Ms. Mayhew and the wider TGS Chemistry Department, with a particular thanks to Ms. King. Thank you very much for listening. We will now take any questions.
Thank you very much, guys, for your presentation. While I'm waiting for some questions to be posted, I'm going to start off by asking a quick question about consumer behavior. You're relying on these lenses to be posted back, and that requires a big change in human consumer behavior. What other incentives, rather than just a discount, can you think of to kind of attract people towards sending these things back?
As well as the sort of monetary incentive, I think the attitude of consumers as awareness of sort of sustainability issues is increasing is sort of causing consumers to want to be more sustainable and to want to, realize the impact that they have on the planet and to try and minimize that. And I think especially as that awareness sort of grows and maybe, things like sharing on social media about, I'm using these responsible, my consumer habits are responsible, and encouraging others to do so. As society shifts towards, focusing more on sustainability, it becomes desirable to be seen as sustainable. And I think that's one of the things that is perhaps an incentive for people to use the product.
Okay, right. I can see quite a few questions posted here. I'm going to start off by asking one, is it possible to make every component of the lens completely biodegradable?
I think that's definitely something we could explore. Obviously, a very important part of the contact lens model is maintaining sterility. There would be a concern if we perhaps replace the aluminium foil with something that would be biodegradable. Consumers particularly would probably have concerns about the sterility of their lens, but it's definitely an avenue we'd be open to exploring. And in the meantime, in the meantime, we have tried to take as many efforts as we can. So for instance, the laminated foil packaging that we've used, the polyolefin lining is actually oxidegradable. The adhesive used is also biodegradable into organic products. So we've tried to account for that as much as we can.
Yeah, and I think whenever something isn't biodegradable, it's reused in our models. So like the aluminium is all collected. There's nothing that sort of goes to waste that isn't either degraded or reused.
Mm-hmm. Another question. Have you thought about have you investigated the theory that the Earth actually manufactures oil, so that the oil is really not a finite resource?
I think even if it's not finite, the rate at which it's currently being produced is probably not enough to satisfy the needs of the population, especially since it's expanding at such a great rate. And I think where we have alternatives to oil, if we have something that we're not sure is a finite resource or not, or something that we definitely know is renewable and, can keep being used, it seems better to use the one that we are sure is, not going to have an impact on the environment and we will not run out of. And also just the general issues around oil with fossil fuel combustion and the impact that has on global warming, it seems better to use more sort of organic materials.
Okay, another question. You said such hydrogels have not been made on an industrial scale before. What is the obstacle for scaling up their production?
So I think the process that we sort of researched was something that had only been developed really recently. It was in a paper released in 2022, and it was about creating fungal-based textiles. And a step in that process was to extract a hydrogel, but in that process, it was then turned into a monofilament. And I think the reason why it hasn't been scaled up or explored so much is because it's a relatively new process. And in terms of scaling issues, I think things like equipment and there's a lot of centrifuging that goes on, and the storage could potentially be an issue, but we try to mitigate that, and we try to look at, what are the alternatives to scaling things up. But a lot of it is quite easy to do on a sort of industrial scale, especially like the sort of cultivation of the fungus that can happen in sort of the bubble column bioreactors, which I think already happens to make sort of like mycoproteins, which they use in like vegan substitutes for meat.
Okay. Another question, what's the shelf life of the lenses? Do they degrade in storage?
No, our lenses would not degrade in storage. We had hoped to do a practical on this, practical experiment, but unfortunately we weren't able to. The lenses themselves, as mentioned in the presentation, would dry out before any degradation happens. The idea of the continuous production is when users go onto, say, the website platform that we've designed so they can interface with our idea, they would create a profile. And on that profile, they would be able to select the number of lenses they want. Because obviously, contact lens users, it's not a guarantee that they would be using a full set of lenses every day. Some people choose to wear glasses. So to cope with that, they would be able to select how many they want. That means that we'd be able to have an accurate idea of how many lenses we should be producing and the rate at which we should produce them. I think another thing we'd have to do is, this is working on an industrial scale and it's in progress, there'd be continual reevaluation within the first few months about how our projected demand compares to the actual amount of lenses that we are sending out and receiving back. So there would need to be a bit of iterative evaluation in there.
And with regards to storage, the actual degradation of the lenses is assisted by the enzymes in the enzyme embedded plastic bag that they're returned in. So without those enzymes, it becomes a lot more difficult for them to degrade. And so when they're in storage and in that buffered saline solution, the temperatures are not high enough and also the enzymes aren't present.
Yeah, and the enzymes, like they have a coating basically, which hides their active sites. So until they until the products are put in the proper industrial conditions, which is a temperature far higher than they would ever reach in normal use or on a hot day or something, until that the coating will not degrade, so the enzymes will not be released and they won't be able to start depolymerizing the plastic.
Okay, I'll take one final question and then we'll have to move on. How will the cost of the biodegradable lens compare with existing lenses?
So existing lenses are copolymerized with silicon, which is in high demand, especially with growing technologies in electronics. This makes it very expensive to manufacture, which means that if all of our sources are biological material for the base of the lens, we can actually manufacture it at a much cheaper cost. This also makes it accessible to more consumers, as well as allowing us, as we've mentioned, to invest in transport that reduces the effect of carbon dioxide emissions through fossil fuel combustion.
And also the fact that we are continually reusing our aluminium and trying to maintain its purity means that as the contact lens production increases, or continues rather, we won't have to continually source more bauxite ore, say, for the aluminium.
Great, thank you very much, Team Javelin, for your presentation and for answering the questions. I'd now like to move on to the next team. So you can stop sharing your screen now. Thank you. So I'd like to invite Team Morphine to turn on their cameras and mics and start their presentation.
Hello, can you see us and hear us?
Yes, we can. Over to you guys.
Okay, so today we're going to be talking to you about our invention, Graphilusk. We're facing a water scarcity crisis. There are over 2 billion people using contaminated water sources. Drought may be the next pandemic. Our solution aims to address Sustainable Development Goal 6, providing clean water and sanitation for all. Through clean water, we will also increase the health of the population by reducing the spread of waterborne diseases. We will also safeguard education, as less girls like us have to travel for miles on end to find water, when they should instead be at school. Better health and education will also lead to more economic productivity, because currently an estimated $260 billion annually is lost globally due to water scarcity. By providing clean water, we will directly improve health and well-being, taking a stride towards improving the lives of these people.
The causes of water scarcity can be broken down. In cities, freshwater supplies are contaminated by sewage outlets. Population growth means that there's not enough water to go around. Coastal communities are particularly vulnerable as climate change and rising sea levels is leading to saltwater intrusion, where freshwater is contaminated by saltwater. On the Bangladesh coast, 5 million people will face river salinity problems by 2050. People in remote communities do not have access to water services. Of the 1.2 billion people lacking even basic services, 8 out of 10 live in rural areas. We urgently need an adaptable solution to providing drinking water to coastal communities, where over 30% of the world lives.
Current water filtration technologies, such as reverse osmosis and more recently membrane bioreactors, face a large limitation. Membrane fouling. Membrane fouling is when organic molecules accumulate on the surface of the membrane, which means biofilms form. This reduces the efficiency and the longevity of the water filter. In addition, current solutions require chlorination of the water to kill the microbes and pre-treat the water. This has detrimental effects on the ecosystem when disposed of. The technologies are also particularly intensive due to intense aeration systems being required for the microbes and pumps to increase the rate of water flow through the membrane.
As you can see here, to come up with a solution with each workgel strand to develop different aspects of the prototype before tying them all back together. Our filter consists of two parts: the mollusks, which pre-filter the water and remove macromolecules that may foul the membrane, and the graphene oxide membrane, which filters out the salts. The coupling of the two creates a high efficiency, low fouling, and low maintenance water filtration system.
The mollusks are natural filter feeders. They remove dissolved organics, bacteria, and heavy metals and incorporate them into their shells, or release them as pseudofeces, which we can easily collect. This pre-treats the water and significantly reduces membrane fouling of the graphene oxide, replacing the need for chlorination. Mollusks keep maintenance costs low, making them economically sustainable for remote areas.
Graphene oxide, abbreviated as GEO, is selected as our membrane material due to its high hydrophilicity and low pressure requirement, which enables its deployment in areas lacking infrastructure and electricity supplies. Its two-dimensional structure and in-plane nanoporosity allow for a low membrane thickness, which removes the otherwise high pressure requirements while enabling higher water flux without sacrificing ion rejection rates. Water molecules are forced through the interlayer channels within the geomembrane under gravity and separated from salt ions at this stage.
Using Fusion 360, we designed a model of our invention with a 5 by 5 meter base and a height of 15 meters, allowing for an area compact design. Galvanized steel will be used to provide structural strength. Recycled HDPE plastic is used for the containers, while PVC tubing is used for the transport of water. However, depending on the area, local resources such as bamboos can be used as alternatives. This ensures environmental sustainability in the manufacturing process. Here's the basic flowchart introducing our subsystems in order that the feed water is treated. The initial input goes to the sedimentation chamber where large particles such as sand will settle. Next, the solution is passed into the biofiltration chamber where the mollusks will pre-treat the seawater by removing organic molecules. The solution is then passed into a capacitor tank containing a pump that transports the seawater to the water tower. The water tower creates hydrostatic pressure to drive the solution through the geomembrane chamber, which removes the salt from the filtrate and expel overconcentrated effluent. The treated water is then stored in our final compartment.
To combat diseases and invasive species, we will prioritize the use of local saltwater mollusks from local waters or markets. Mollusks demonstrate long lifespans of 5 to 10 years, with some species living up to 20 years. Thus, we anticipate the periodic check-ins by community volunteers will suffice, as they would not require much replacement. The graphene oxide membrane also does not need to be replaced very often due to effective reduction of membrane fouling by the mollusks, and the replacements are relatively cheap, costing around $50 per membrane.
A water pump is used to pump the water into the water tower to generate hydrostatic pressure for desalination. The energy required is significantly less than the other methods, such as distillation. This makes the pressure generation device easier to acquire. Moreover, the energy can be sustainably obtained from local sea resources, such as by the means of tidal and wave energy. Overall, the maintenance cost roughly only $30 per year. And one Brevlosk with specification shown before would be a perfect potable water provider for a small community of population around 3,000 people. However, Brevlosk yields potentials to be scaled up to regional and even national levels using an array of Brevlosks with larger parameters.
So how will our invention uniquely and effectively promote sustainable development, as illustrated by the 5 Ps published by the UN? Our invention provides clean water directly to the people in need, supporting the front lines of fighting waterborne diseases. Every dollar invested in water and sanitation yields a $4 economic return according to the United Nations, lowering healthcare costs, increasing productivity, and reducing premature death. Not only does our invention have a lower energy consumption, we also aim to reduce waste by working with local communities to use brine for salt making and pseudofeces for agriculture. and using recycled plastic and steel for making a water tower. We will also partner up with local communities and governments, producing user manuals and training programs for the setup and maintenance of the filter. Finally, our invention also contributes to peace by preventing resource-driven conflicts, like the disputes over the Kaveri Basin in India.
In the future, we need to address some of the limitations of our current prototype. The geomembrane can be modified further to improve its longevity and performance. Geosheets could be further reduced via hydrothermal means to increase its conductivity, which enables the electrochemical removal of organic molecules and bacteria, which reduces fouling via electrostatic propulsion as well. Additionally, geo can be intercalated with rigid and anisotropic conjugated small molecules such as TBO dyes, which allows for the fine control over the interlayer spacing and two-dimensional in-plane permeation pathway of the geomembrane. In addition, pi stacking and the introduction of ions like K+ ions will effectively avoid geomembrane swelling. This increases the separating performance of the salt from the water. The transport of large geofilters may also be burdensome, so we propose to address this issue by origami folding for compactness.
Our invention, Grapholusk, is revolutionary because it addresses membrane fouling, the Achilles heel of current water filtration systems. We calculated the optimal water flow rates in the subsystems using mathematical modeling ranging from the Stokes equation to CFD simulations of sedimentation. Our conclusion is that the Grapholusk system will generate 6,000 liters of potable water per day, and this can be scaled to meet different water demands. As you can see from this table, we have estimated that compared to traditional water filtration methods scaled to the same efficiency, Grapholusk would have a significantly lower initiation, operation, and maintenance cost, and a low energy demand of 700 kilojoules per day. With some further research, our team believes that Grapholusk would be able to contribute significantly in combating water insecurities in communities threatened with saltwater intrusion. Thank you very much for listening. We're accepting questions now.
Thank you very much, Team Morphine, for your interesting presentation. I've had quite a few questions posted here, so I'm going to just work my way through them. So first question, how do you know that the mollusks will eat that particular food? And how do they keep them alive when the plant breaks down?
So mollusks are very low maintenance and they filter feed pretty much everything in the water. That goes from bacteria in the water to organic molecules. And we know that saltwater has lots of these, and saltwater mollusks that live in local waters are very efficient at filtering the local contaminants within the seawater because that's how they live. In terms of how the mollusk will live if the plant breaks down, well, presumably we wouldn't want the plant to break down, but if it did, the cost of replacing the mollusk is not high. And also they're able to survive stressful environments for an extended period of time. So if we're able to get it fixed very soon, then the mollusk likely won't die.
Mm-hmm. Just following on from that question then, how long does the water need to be stored with mollusk before it can be sent through the filter?
We have used several mathematical modeling skills, such as by establishing equations and calculating the various parameters we introduced, which we include in the report. And we calculated that it would take around 2 hours for the mollusk in our specification to purify the entire tank of water. And we calculated that overall, the rate determines that it's not the mollusk, it is actually the geomembrane. So the filtration rate of mollusks would not actually matter significantly due to our water rate calculation. And that is the optimal water rate flow we've calculated that results in an output of 6,000 liters a day.
Okay. Another question. What are the optimal conditions for the mollusk activity and well-being, and how will these be maintained?
So the mollusk optimal activity, because these are local saltwater mollusks, the optimum temperature is actually just the temperature of the sea and the seawater that comes in. So we won't actually have to, like the point of our system is that it's low maintenance. So it's actually done, it will be done at room temperature, but just with a constant flux of water. And that creates a really good environment for the mollusk. Obviously, periodic monitoring of the pH and of like conditions within the water and of like contaminant concentration within the water will be monitored, but we anticipate that it will be low maintenance.
Okay, just another question on the mollusks again, especially how would you source them, and especially on a large scale, would this add to the carbon footprint of the process?
So the idea is we're targeting in coastal communities, and we're hoping that the coastal communities that we're targeting will generally have mollusks farm, and we're trying to source all the mollusks locally. The mollusks found in the area will be the ones most efficient at removing the pollutants of that area.
Mm-hmm. And the other thing is you talk about using sort of wind power to power your pumps. Have you considered solar power as well?
Yes, we have, but I think the purpose of that is we should use a sustainable and renewable energy mainly, and it will be even better to use the locally sourced renewable energy resources, because we're targeting the coastal communities. So we believe that the use of tidal and wave energy would be very effective, especially in many areas that would have been already developed. So that would not even contribute to our cost, because the source is already there.
We also thought that because the water tower is quite high, you could actually just like attach a wind turbine at the top, and that would be able to generate the electricity needed. But obviously any source of sustainable energy is a good source of energy for it, and not much is needed.
Okay, there's still many questions here, but unfortunately we need to move on because we're tight on time. Thank you so much, Team Morphine, for your presentation and answering the questions. I'm now going to invite our last team to do their presentation. So this is over to Team Flavonoids from Benenden School to present their project.
Thank you, Osha.
Yep, we can see your screen and you can see your slides now.
Okay. And thank you for having us. We just finished our GCSEs the day before yesterday, and we are so excited to be here presenting our project to you all. With our invention, we set out to tackle the problem of antibiotic resistance, which poses a great threat to the Sustainable Development Goal of good health and well-being. In fact, according to the World Health Organization, antibiotic resistance is one of the biggest threats to global health, food security, and development. A growing number of infections are becoming harder to treat, which is putting massive strain on hospitals, also causing over 4.95 million deaths in 2019. It is clear to see that this is a massive threat to health and well-being, so it is vital that we tackle this problem.
I also began by researching sustainable antibiotics. We decided to use flavonoids, which are phytochemicals found naturally in plants, and because the flavanol found in many plants which grow in the UK, quercetin, has high antibacterial activity. We chose the plants which had the highest concentration of this flavonoid, and after calculating the expected concentration of flavanol per gram of soap, given our research methods, we decided to test our solution. We made 9 different flavonoid extracts using ethanol as a solvent and evaporated these until they were 30 ml each. We then made our soaps. We made cold processed soap to keep temperatures below 60 degrees C to prevent our flavonoids from degrading. We added 1.3 ml flavonoid extract to each 50 ml soap, which allowed us to reach the minimum inhibitory threshold of flavonoids. After letting our soaps cure for 3 weeks, which gives time for all the ethanol to evaporate, we tested each of our soaps 3 times using Raman disc against Staphylococcus aureus, as well as a control soap with no extracts from Dove soap, so that we could compare the antibacterial activity of our soap with a commercial soap.
We had a number of objectives to achieve our goal of reducing levels of antibiotic-resistant bacteria. We aim to make our soap sustainable by using plants sourced from and native to the UK, which are naturally high in flavonoids, our chosen antibiotic. We also aim to reduce levels of antibiotic-resistant bacteria and therefore reduce the strain on health through our use of flavonoids. Flavonoids have been shown to be effective against antibiotic-resistant bacteria such as E. coli and Staph aureus, and have also been shown to, quote, reverse antibiotic resistance. Our solution aims to curb transmission of bacteria, and by making our soaps and testing them against bacteria, we were able to show that all of our soaps had a larger area of inhibition compared to Dove soap, and so would be more effective and an effective alternative to everyday hand soap.
Our solution to an increasing global threat of antibacterial resistance is to create a sustainable flavonoid soap, which can be used in place of current hand soaps. In recent studies, flavonoids have been shown to be effective against many multi-drug resistant bacteria, which gave us the idea of extracting flavonoids ourselves and applying them to help solve the problem of antibiotic resistance in health. Our flavonoid extracts were most effective when we used oven-dried plants, which we dried at below 60 degrees to prevent degradation of the flavonoid compounds. We chose a variety of plants with the highest concentrations of the flavanol quercetin, which has many antibacterial effects. It damages cell membranes, inhibits quorum sensing and biofilm formation, and inhibits bacterial gyrase. Gyrase plays a role in the synthesis of nucleic acids and is a popular target for antibiotics. The structure of flavonoids is what makes them so effective. They may bind to the same site as ATP on gyrase, preventing the supercoiling activity of gyrase, which is ATP dependent. This activity makes quercetin effective against multi-drug resistant bacteria and makes it a useful compound to use in our soaps. The hydroxyl groups on the aromatic ring in flavonoids are also proven to improve antibacterial activity. Additionally, through hydroxylation, chemical solubility of the flavanol is improved, which is also proven to increase the antibacterial activity.
We made the production as efficient and sustainable as possible, aiming to address all 5 Ps of sustainable development. First, people. Our soap will be used to reduce transmissions of bacteria and prevent antibiotic resistance. This helps to prevent people from getting ill from untreatable infections and improves quality of life. Secondly, planet. By using locally sourced plants, we reduce the environmental cost of transport. We also use the optimum concentration of ethanol and ratio of solvent to plant material to extract the highest proportion of flavonoids possible from our plants. We also aim to reach the minimum inhibitory threshold of flavonoid of soap. And although we had no way of actually finding this, we calculated that we should be close to this level. By keeping the concentrations of flavonoids at this threshold, we also reduce the risk of antibiotic resistance. Antibiotics are usually dispensed at the minimal inhibitory concentration. Prosperity. By reducing antibiotic resistant in bacteria in the population, our soap would reduce the strain on health. This would reduce the number of people needing medical treatment for resistant bacteria, which can have lengthy hospitalization times and can be very costly to health. Our soap would reduce the costs that this problem poses on the NHS and increase prosperity. Our soap could be used in developing countries and areas of conflict as a cheap solution to prevent the spread of bacteria. It reduces transmissions of both antibiotic and normal bacteria. We were able to show that our soaps containing flavonoids extracts had higher antibiotic effects than those not containing our extracts at both 24 and 48 hours and in different concentrations. Partnerships. We applied for an award at our school in which we'll be able to partner with a successful school alumnus who could help us improve the sustainability of our solution. Furthermore, we believe that it could be very useful to work with other organizations in partnership that aim to increase sanitation. And here are some of our results. There are 2 graphs showing how, on average, our soaps were more effective than others without flavonoids.
To test our soaps further, we will compare the areas of inhibition when tested against gram-negative bacteria to results of a test against Staphylococcus aureus. Generally, gram-negative bacteria are less affected by quercetin than gram-positive, due to differences in their cell membranes. Although some quercetin derivatives are more effective against gram-negative bacteria, ideally our soap will be effective against both to have a greater impact on health. In order for our soap to be effective in reducing bacterial transmission, we also need to promote hand washing. We aim to do this through our packaging and logos, which are designed to be appealing to a customer. If we're able to win the Atherton Award at our school, we will be able to speak to a successful school alumnus who will help us promote our solution to increase hand washing, as well as advertising our soap to achieve our goal of reducing bacterial transmissions. On top of this, we would like to test more plants in the future to compare how effective each one is, also so there'll be a larger variety of soap for customers to pick from if they do get released to the market. Although we did not focus on this in our short paper, casting also has high antifungal and antiviral activity, which has been shown to be effective against COVID-19. This will increase the impact our solution will have on SDG of health, and is something we would like to research further.
Thank you all so much for listening and any questions.
Great. Thank you so much, Team Flavonoids, for your fantastic presentation. I've had quite a few questions posted, so I'm going to work my way through them. So first question, how does your soap address the good bacteria that are present on human hands? Are they killed too?
So we'd have to test this, but we were looking at many studies on harmful bacteria, and that's the goal we'd like to address. We are testing this further. We'd also like to partner with other soap companies to see how this would affect other bacteria.
All right, just sort of moving on, sort of in that theme, another question. Since antibacterial resistance is more likely to increase with exposure, should we not limit the use of flavonoids? And sort of how do you propose to prevent the bacteria from developing resistance to these flavonoids?
So flavonoids have been shown to reduce antibiotic resistance, and I think this is really due to their varying structures. And that means that it can be difficult for the bacteria to become resistant to them. And we would try using different flavonoids as well and incorporate those into our soaps, because we were focusing on plants sourced in the UK, and the plants that we chose had really high quercetin. But we also tried camphor, and we created a soap with a combination of both, and using combinations of flavonoids could make it harder for antibiotic resistance to occur.
Okay, another question. How does the antibacterial effectiveness compare to ethanol-based hand gels?
So generally, we chose soap because soap has been shown to be more effective than gels, but our antibiotic activity is mainly attributed to flavonoids because the ethanol would evaporate. So whereas the ethanol would kill things in hand soap, for us it's the flavonoid, and that's what we've got focused on. And I think comparing how they would affect different bacteria would also be useful, because we compared different soaps as the market we were looking at, and it'll be good to compare to other things as well.
Okay. Well, another question. A key part of the soap properties is the sensory impact. Have you considered this?
So just to clarify, this is talking about sort of color, texture, odor, that sort of thing.
Yep.
And so we have considered this because it's important to promote our soaps to look nice as well, to encourage use. So one of the extracts of a plant we used, as mentioned, was blackberry, and this has, and many of the plants we used had natural colorings in it, meaning that our soaps naturally formed nice looking colors, arguably. However, we did take into account that, for example, we used dill and onion, and these weren't particularly nice scents for soaps. So we are looking to, as mentioned before, test other plants and vegetables and fruits, particularly focusing on those ideal for a market and to use in a soap for the more sensory attributes.
Okay, so we're kind of coming up to the end, but there's a couple of more questions I'm going to try and squeeze in. The one question which says the biological mechanism presented are very convincing. What additional toxicology work do you foresee to ensure product safety?
So we would again have to test on other bacteria, as you mentioned, with bacteria that occurs naturally on your skin. And as well, we'd like to look closer at how different concentrations of flavonoids affect antibacterial activity. And we would do that by improving our method, because really for our method, it was limited by what we could do, and we could only use ethanol as a solvent and really limit how we extracted it. So we'd like to do that and then see how this impacts different bacteria.
Okay, one last question, and then we'll have to wrap up. How would the plant resources be disposed once a flavonoid has been extracted from them?
We plan on, so luckily plants are biodegradable. So we plan on composting all of the remains that don't contain any chemicals, and this can ensure that there is little waste to our invention and our production of the soaps.
Okay, brilliant. Well, thank you so much for your presentation and for answering the questions. We're now going to take a short break. So everyone on the call, please do stay on the Zoom call. Just mute and turn off your cameras. The panelists are now going to leave the Zoom call for a short discussion, and we will be back in roughly 10 minutes to continue. So please stay on the call, don't leave, and we will join you back in 10 minutes. So just everyone go and have a stretch of legs and make a cup of tea. See you shortly. Hello, everybody. We're back, and we're going to continue with the webinar now. I'd like to introduce Deborah now. Hopefully, Deborah's joined. Oh, yeah, Deborah's there. Deborah Grubb, who's going to now give a presentation about her career in chemical engineering.
There you go. Thank you, Cameron. And good afternoon, everyone. It's still morning here in the United States, but it's a pleasure to be with you all. And hopefully my slides will come up shortly here. I have a lot of photographs and pictures to share with you today. And so it may take a while for them to come up. There we go. I think it's working now.
Yeah, they haven't come up yet.
So it's a real honor for me to work with you today and
Hi, Deborah. I don't think your sound's coming through. Ah, I think we're going to probably lost Deborah there for a moment. She'll probably join us in a moment again. Just everyone bear with us while Deborah reconnects.
I'm back.
Yes. Hi.
It dropped me.
Yes.
Those over the ocean gremlins. Let's try this again.
Okay.
All right. I think it says it's loading. Can you see me?
I can
All
see
right.
the
This
screen
is
now.
good.
Great.
All right. We're going to present mode, and we will move quickly through the presentation. I was telling tales out of school. So anyway, chemical engineering has changed my life, and it's my real honor and pleasure to be with you today to tell you about all the wonderful things that engineering involves. Chemical and bioengineering is all the stuff you can read there. So if you enjoy your work, you're going to do better at it. And if you do better at it, you're going to be more productive. And if you're more productive, you will find success. So let's see what chemical engineering is all about. It all started here back at Addison Trail High School in Addison, Illinois, and a long time ago. And I'm here today because a math teacher suggested engineering to me, and you can see him in the lower right-hand corner of your screen. That's Bill Verkus with one of my classmates, Laura Chen, and we had a wonderful time, and it was Bill that suggested engineering to me. And that's how I ended up at Cambridge. But first I had to go to school at Purdue and study chemical engineering, and you can see various pictures of my classmates and graduation, and also me doing a little bit of summer job work. It's very important to get engineering internships to learn about how you can learn about engineering before you actually have to have a full-time job. I also had a summer internship with Amoco Oil, which turned into BP, and that'll show up a little later too. But as you can see, I was the short person at the refinery, and it was fun. But I learned a lot about safety when one works with oil and gas. After graduation, I went to work at DuPont in East Chicago, Indiana, and this was what I had to wear when I had to sample reactor off gas of a chlorosulfonic reactor. And what I learned about work is that work is work, but work is also fun. In the right-hand picture, that is the DuPont Foster's Lager Memorial Cup softball team. And I was literally and figuratively the short fielder. And you would say, there's not a lot of women in that picture. And I'd say, yes, because there were not a lot of women in engineering way back in the dark ages. So then I get to go to Cambridge, and we had fun at Cambridge, as you can see from the picture in the upper left. I was at Churchill College, and it was really a wonderful experience and opportunity to go to school and be with people who were from all over the world. And of course, in the lower left-hand corner, you will see Nigel, who was one of my classmates, and you will see him a little later today. And of course, who can forget Fitzbilly's? If you were a student at Cambridge, or if you've been to Cambridge, you have to stop at Fitzbilly's for the sticky buns. They are absolutely fantastic. After Cambridge, I went back to the United States and worked for DuPont at Edgemoor. And the teams will recognize the fact that the Edgemoor plant made titanium dioxide and also had ferric chloride on it. And I was one of the first women engineers on that site, and I was known as the wastewater woman. And because I was dealing with all of the waste. And so that's how I learned about ferric chloride in titanium dioxide in water. And you can see on the right-hand picture, work was work, but work was also a lot of fun. Then I did some construction work in New Jersey, where I was a construction engineer. And I learned in chemical engineering how to design and what went on inside distillation columns. And that's what you see in the picture on the left. And on the picture on the right, the column is being put down on its anchor bolts, and you can see that happening. I am the farthest person on the right-hand side of the picture. That's me. It was a low budget. I did not have to get dressed up to go to work, but I learned how to take down and put up distillation columns also, and not just how to run them. Then they said, well, Deb, you're doing so well doing construction. Let's go ahead and go and do the rest of do some other construction. So I was transferred to Wilmington, Delaware, and worked on an agricultural biological laboratory. And you can see that being built right here. Then I said, well, you're doing such a good job. And this was the big job. This was a $92 or $82 million back in 1982. Laboratory that was going to do pharmaceutical research, and it involved parenteral drugs, which were injectable drugs, and also studies with respect to animals. And so this is my team. You can see me in my office in the lower left-hand corner. You can see a couple of the engineers that were reporting to me in the right-hand corner or upper right. And then that's some of us with the contractors as the building is being constructed. It was a lot of fun. And I got that job because I asked a lot of good questions. Then I had an opportunity to lead a Kevlar expansion in Northern Ireland. And I actually got the job because I had lived in the UK. So this is where exposure at Cambridge, actually, and my exposure to the British culture and the British system actually helped me. And so you can see a picture of Kevlar. It's a gold fiber, and it can be dyed in different colors. It's in bulletproof vests, and Kevlar has saved thousands of lives around the world because of its properties. And that's me in front of the DuPont Motel. During that time, unfortunately, there were troubles in Northern Ireland. And so we were housed either at the hotel or in the nearby town. I had an opportunity to help the United States Army and get rid of, or demilitarize, as they call it, the U.S. chemical weapons stockpile. And that involved a number of trips, one of which was to Johnston Atoll, which is about 800 kilometers southwest of Honolulu, Hawaii, in the Pacific Ocean. And this is a picture of Johnston Atoll. And so this was the demolition of the chemical weapons. And you can see some mortar shells behind us there in the picture on the bottom, where we have rendered everything harmless. And I'm happy to report that at this point in time, the United States chemical weapons stockpile is nearly totally depleted and gone, been destroyed. I then got some manufacturing assignments, and I worked with teams in Europe, both in Spain and in Luxembourg. And you can see the Spaniards and me up on the upper left, and the Luxembourg plant where I had some Tyvek manufacturer. We were doing some nonwovens. And so Tyvek is a hazardous manufacturing process, and safety is extremely important. Also got to travel and work in China and India as part of that job. And so there's a picture of me on the Great Wall in the lower left and riding an elephant. And I always thought, well, am I going to fall off the elephant? And what I found out was elephants are so wide that there's no way you can fall off if you have any balance. And I really loved learning about the Chinese and the Indian culture. And that knowledge has served me today, even as I own my own business. I then went to work for BP. I retired from DuPont, went to work from BP, and worked from Alaska to Azerbaijan. I was based in London. And so again, and the BP people told me that they hired me partly because I had gotten experience at Cambridge and also the experience working in Northern Ireland. And so the picture on the lower right is me and standing in front of some government buildings in Azerbaijan and meeting with an offshore crew there. Because I got to do work in the Caspian. So I went
I think we may have lost Deborah again. Connection may have dropped. Apologies about this, everyone. Yes. We'll give Deborah one more, just a minute, see if she can rejoin. I think Deborah's connection may have dropped. So we could move on because we're getting quite close to 5 o'clock as it is. So maybe we can move on and maybe invite Nigel Hurst to come and present the outcomes from the judges' discussion and tell us a little bit about the IChemE.
Okay, thanks, Cameron. And well, first of all, my warmest congratulations to all the teams. The judging panel were blown away by your enthusiasm, creativity, and everything else. Before I announce the winners, or the runner-up and the winner, I'd just like to say that, you know, I too have had a great life in chemical engineering, and there has never been a better time for young people to consider chemical, biochemical, electrochemical, and all the other chemical disciplines in chemical engineering. And if you want to find more about it, there's quite a lot of information on the IChemE.org website, and I encourage you to look at that. But anyway, enough from me. You want to know who's won and who's the runner-up. Well, first of all, the runner-up, we've chosen unanimously Project Javelin. Very well done. We liked your life cycle analysis, and we liked how much you tried to make it easy for people to adopt your scheme. It reminded us very much of the coffee pod recycling systems which are available these days. So that was great. We enjoyed that. The winner, again, this was a unanimous decision, and it is flavonoids. We particularly liked your full cycle of experiments. We liked the simplicity of your idea and how you'd explored all aspects of it. And we also liked the way that you answered the questions even when you clearly didn't know the answer. So well done for a thorough understanding of your subject. So I've got a certificate I've written out for you. You'll get the real one when you spend your 2 days in Cambridge, and I would thoroughly recommend that you make the most of that time because the advantages of an Oxbridge education are, as Deb has said, immeasurable and lifelong. So here's your certificate, which we've written out. I hope you can see it, and very well done.
Team Flavonoid, come online, turn on your cameras and mic.
Thank you so much. That's very good.
Well done, guys, and congratulations.
Thank you.
It's been really fun doing this project.
Great, great. Just as Nigel mentioned, as winners, you'll be invited to Cambridge to come and spend a couple of days here. But in addition to that, there is a cash prize as well, and we will be sending you each a £100 voucher to spend as well. And so Alan will be in touch about that. So congratulations, guys, again. Just to also say thank you so much to all of our teams that have contributed towards this competition. And thank you for everyone's hard work and effort. It's been great to engage with so many students and schools. It's been fantastic to see some of the creativity and ideas that some of the students have come up with. I hope this has been an extremely valuable, academically enriching program for you all. And I hope this has encouraged you to think about chemical engineering and biotechnology as a degree, as a subject to study in higher education. Last but not least, I just wanted to say thank you again to Nigel Hurst, Deborah Grubb, Peter Davidson for joining us today on this webinar, and for all of your support and contribution with this competition as well. And Andy's there. I don't know if you want to say a few words.
No, I was just going to say thank you very much. Well done, everybody. All the groups as well. Some really good answers to the questioning that you got. So it's great to hear all that new ideas. Thanks.
So with this, we'll end this webinar. I hope you all have a fantastic summer. There is the University Open Days happening on the 6th or 7th of July. I hope many of you will come along and visit Cambridge then as well. And best of luck with your exams and your studies and your future aspirations in higher education, guys. Thanks, everybody. Bye.